We are in section 3F, and we're now going to look at differentials, which are very closely related to the idea of linear approximations. A differential is basically just a way of approximating the change in the y value as the result of a small change in x. Let's start by looking at a diagram. If I just arbitrarily pick a point on here, I'll call it x. Excuse me. And then I move over a little distance, and I'll have to make it big enough so I can see everything. So we'll imagine this to be a small distance. I'm going to call that small distance that I've moved over the change in x. We often use delta to signify a change, the Greek letter delta. So delta x is going to be our change in x. It's similar to what we called h before when we were doing derivatives. So this new x value would be x plus delta x. That, of course, corresponds to a new y value on the graph, right about here. And so if I call my original y value f of x, then this new y value would be f of x plus delta x. When we moved from x to x plus delta x, the y value changed from f of x to f of x plus delta x, and we usually call that change in y delta y. So notice, excuse me. All right, let's try that again. In order to actually calculate that value of delta y, or the change in y, we just subtract f of x plus delta x minus f of x. All right, now let's think about the same thing, but instead of following the curve, we're going to follow the tangent line instead. So I'm going to sketch in the tangent line here at my original point, x, f of x. And just like the y value changed on the curve, the y value also changes on the tangent line. So again, the original y value was right about here. And on the tangent line, we changed to a new y value right about there. This distance that the y value changes along the tangent line, we're going to refer to as dy, the differential. And my goal right now is to figure out how to calculate dy. In order to do that, let's keep a couple of things in mind. First of all, this distance right here that I drew is the same as the delta x. So this is really delta x. And then I've already labeled that vertical distance dy, which is what we want to call it. And then I'm also going to remember that since this is the tangent line, the slope of this line would be the derivative, f prime of x. Since slope is also rise over run, I could write that m, or f prime of x, is the rise, dy, over the run, delta x. And that means that I could solve for the dy by just multiplying the delta x over. And f prime of x delta x is equal to dy. So to calculate dy, I can multiply the derivative, f prime of x, times the change in the x value, delta x. All right. If these 2 points are actually pretty close together, if delta x is close to 0, you can see that the dy and the delta y would be approximations for one another. They're close to the same value, again, especially if we stay closer to the original x so that the tangent line is very close to the curve. So we're going to say that the dy can be used as an approximation for the delta y. So if I'd like to know the change in a function's value, the change in y, I can approximate it with f prime of x delta x. All right, let's try an example. If my function is f of x equals the natural log of x, what is the approximate change in f of x, or y, as x increases from 1 to 1.2? So we're going to say the approximate change in y tells me that I really want the differential, the approximate change, right? And I calculate that by taking f prime of x delta x. In this case, the derivative, f prime of x, would be 1 over x delta x. And then I'm just ready to plug in my values. My values I can find over here. X increases from 1 to 1.2. So my original x value would be x equals 1. That's where we started. And then the delta x, the change in x, would just be 1.2 minus 1, or 0.2. And I'll just take those values and plug them into my differential calculation. So x started at 1, delta x is 0.2, and dy is 1 times 0.2, or 0.2. So it looks like when x goes from 1 to 1.2, the natural log of x is also going to increase by about 0.2. All right, let's look at a couple of other examples that perhaps might show us where this could be handy. This type of calculation is often used as a fairly quick and easy way to make an estimate of how measurement error can affect calculations. Whenever we measure something, we always know that we can only measure to a certain degree of accuracy, right? It depends on, what kind of measurement instruments we have, how good our eyes are, how good we are at it, all those kinds of things. But ultimately, we have to decide, are we going to round off to the nearest centimeter, or the nearest millimeter, the nearest inch, whatever it might be. And by choosing to round off, we always are choosing the degree of accuracy of our measurement. When we have a measurement accurate to within a certain amount, we have to say that every time we use that measurement in a calculation, the calculation then also has a degree of accuracy. It has a certain amount of error that may occur due to the error in measurement. We're going to use differentials to approximate that error. So if we look at our first example, the radius of a circle is measured as 5.1 centimeters, but we've rounded to the nearest tenth of a centimeter, the 0.1. And notice that what that actually means is that the real radius must be within 5/100ths of the measurement, right? If you think about this, we measured it at 5.1 to the nearest tenth. So there's 5.0 and there's 5.2. That means that my actual measurement could be off by as much as 5/100ths either way. If it was off by more than 5/100ths, I would have rounded up. And if it was rounded off by more than 5/100ths this way, I would have rounded down. So I could be off by as much as positive 0.05 this way, or as much as negative 0.05 that way. So that's really what rounding to the nearest tenth means. All right, so this tells me right away that my radius is measured at 5.1, but the possible error, the delta r, is plus or minus 0.05. So I get those values right out of the problem. I'd now like to approximate the maximum error in the calculation of the area of the circle. Well, of course, to calculate area, we use pi r squared. And so I'm going to say the approximate, well, the actual error, delta A, can be approximated by the differential, dA. And then I'm just going to use the same formula adapted for my variables. So instead of f prime of x delta x, I would have a prime of r delta r. So again, same thing, just adapted for my variables. So let's see, a prime, that would be 2 pi r times delta r. And then I'll just plug in my values. 2 pi times 5.1 for r times plus or minus 0.05 for delta r. And let's see, I did that one. It gave me plus or minus 1.6. Now that's an area, so that would be square centimeters. And notice what this says. With a possible error in measurement of 5/100ths, my area calculation could be off by as much as about 1.5 square centimeters. So just a really good illustration that small errors in measurement can create relatively large errors in the calculations that we use them for. All right, let's try another example. This one's more of an actual change example as opposed to an error in measurement. I'm looking at the ideal gas law. Usually you study this in chemistry. PV equals nRT. N and R are simply constants based on the number of molecules of gas and a physical constant R. So in our problem, we're going to just replace nR with 0.06 for the purpose of this problem. It's just a constant of some kind. So I'm going to rewrite this as PV equals 0.06T. P stands for the pressure of the gas, V is the volume, and T is the temperature. All right, in part A, we have a gas at temperature 300 degrees Kelvin with volume 6 liters and pressure 3 atmospheres. For constant volume, suppose that the temperature is increased by 0.05 degrees. What is the approximate change in pressure? So let me start by just focusing on the fact that I want the approximate change in pressure. That means I really want an equation for P. Ultimately, I want to find dP. So let's start working our way toward the equation we want to use first, and then we'll deal with the differential. So I'm going to go back up here to my equation, and I'm going to notice that, first of all, in this problem, the volume doesn't change. There's a constant volume. So this volume of 6 liters is going to stay the same all the time, and I'm going to go ahead and just put that into my equation. So P times 6 equals 0.06T, or P equals 0.01T. I've now got an equation for P, which I need in order to find dP. So dP, and again, I'm using the same equation for differentials, right? F prime of x delta x, but I'm going to put it in terms of these variables. It would be P prime of t delta t this time. P prime of t is actually a constant in this case, 0.01. And delta t, well, the temperature went up by 0.05 degrees, so positive. And let's see, that's just going to give me 0.0005 atmospheres. All right, so there's our change in pressure, it's approximation, but our approximate change in pressure for an increase of 0.05 degrees. All right, in part B, we have a related problem. Still have a gas at a temperature of 300 degrees Kelvin, volume 6 liters, pressure 3 atmospheres. But this time, I'm going to say, what if we keep the temperature constant? So that temperature is a constant 300 degrees, and the volume is increased by 1/10 of a liter. Now what's the approximate change in pressure? So we'll go back to our original equation. PV equals 0.06 T. And since my temperature is constant, I'm going to put the 300 in for T. So PV would equal 18. Ultimately, I want the approximate change in pressure, so my goal again is to find dP, meaning I want to solve my equation for P. So P would be 18 divided by V, or since I know I'm going to have to take a derivative, I might want to think of that as 18V to the negative 1. All right, I think I have everything I need. dP, in the variables I have now, would be P prime of V delta V, which is going to give me negative 18 V to the negative 2 times delta V, or negative 18 delta V over V squared. We'll plug in the values from the problem. Delta V, my volume is increasing by 0.1. So delta V is 0.1. And the volume itself started at 6 liters, so I'll use 6 for V. And that gives me negative 0.05. Again, in atmospheres. So there's the math of it. Let's just think about what happened for a moment. In part A, we increased the temperature, and we got a positive, so an increase in pressure. Makes sense, right? If you heat up a gas, it exerts more pressure because the molecules are moving faster. In part B, we increased the volume. If you imagine a gas trapped in some sort of a space, and you give it more space, the pressure is actually going to go down. And that's why we got a negative dP, or a negative change in pressure for part B. All right, that brings us to the end of topic F.